you, John. Thank you, everybody, for coming this morning. I also want to thank Kathy for printing out the flyers and getting good publicity out there. So this is a takeoff on Buzz Lightyear to Petabytes and Beyond, how I do data management with CESM. So here's my outline. I'm going to start off with just a little bit about me, CSM and big data, since that's a big thing now and has been for a couple of years. How we do, or I do, data management and the tools and policies and practices that I follow, and then where I think CSM data management is going to be going into the future. So as John mentioned, I started as a student assistant, and thanks to the NCAR library, they've scanned in all the old staff notes, and this is actually the job ad that I applied for. And it says AAP, that's because CGD used to be called Atmospheric Analysis and Prediction. And as you can see, the princely rate of $6.90 an hour, which was far superior than the $4.45 I was making at food service at CU. But anyway, I think that the irony is it says operates as needed computer programs for the storage and processing of data. It's still what I do now. And skill in handling large data sets, which back then was like, 10 megs, 50 megs, 100 megabytes, something like that. And skill in transferring data between the computers, mass store, and physical tape. Again, a big part of my job today. So basically what I do is provide general data management for CSM. That involves like auditing our holdings, auditing our disk space, keeping track of where all this data is, answering questions about it from people within CGD, people within NCAR, people outside NCAR, our user community. I've worked as a liaison to other groups that inside NCAR and Department of Energy, which funds me, and other internal and external data focus groups. There's a group called the Global Organization for Earth System Science Portals that I've given a number of talks to. Occasionally I'll review a paper. I've actually written one paper once, which was nice. I got to go to Singapore for that meeting. It was supposed to be in Japan, but then they had the big earthquake, so they went to Singapore. That's a long flight. You don't want to do that. 7 years ago, I gave a talk at ICAS, thanks to Al Kelly. It was very special to me. I supervise data publishing and post-processing, and I'll explain what that is here in a minute. I mint digital object identifiers for our data sets using the DataSite service. Generalized computing support for our staff and anyone else that happens to ask me. I am a member of AMS, AGU, and NUGEX is the NERSC Users Group Executive Committee. I'm one of the DOE representatives for them. I've been to both AMS and AGU and have given talks about data and so forth there. Oh yeah, occasionally I do some coding. I have a big stack of Fortran codes, yay Fortran, that I use reasonably regularly. So everybody knows what CSM is, but if they don't, it's this gigantic monster blob of code, about 1 million lines. This is a little bit different schematic than the one you're used to seeing. This was done by a woman who was working with Steve Easterbrook, who visited here a few years ago. He was doing a survey of climate model software engineering practices. And the interesting thing I like about this diagram is the bubbles are roughly proportional to the size of the data, or size of the code. So you can see the atmospheric model is by far the largest, although Dave will probably tell me that CLM is a lot bigger now. And so this, as all these things do their thing and compute the state of the climate, they dump out data. Lots and lots and lots of data. So here's an example, or here's the numbers going back the last 20 years or so of how much data we archive out of this model. And I've broken it up into two parts. What's located at NCAR on our tape archive system here, primarily under our /CCSM root directory, and then what we have located from model runs elsewhere, primarily at NERSC in California, Argonne near Chicago, Oak Ridge in Tennessee, and NCSA, National Center for Supercomputing Applications, near the University of Illinois. So you can see over time, you go back to 2004, it was maybe 50 terabytes or something like that. Whereas last year we had a new peak, approximately 1.6 petabytes of data archived to our HPSS. And 2016 was a bit of a dip. And then it was early in 2017 that Dave gave us a talk about, Dave Hart gave us a talk about, please restrain from using HPSS so much. So what did CGD do in response? We added more than we ever did. So obviously that didn't work so well. But anyway, so then you add in what we've saved at other centers. And so last year we hit about 2.2 petabytes total of archive space. And you may be wondering what these bumps are. So down here in the 2004 to 2006 range, that was this thing called CMAP 3, coupled model intercomparison project number 3. That was big for its time, and now it's like, who cares? This big bump in the 2010 to 2012 range, that was the infamous CMAP 5. I'll talk more about these two later. And then the last few years, it's been what we call these community projects, which are very large-scale campaigns or sets of runs that we do that don't have anything to do with one of these model intercomparison projects, but which can generate amazingly large amounts of data. So if you add this up over time, so right now, currently on our HPSS, under our primary directory, we've got roughly 7.3, 7.4 petabytes of data. Scattered elsewhere on the system is another couple petabytes. You add in everything else that we have elsewhere, so we're talking on the order of more than 12 petabytes, or roughly 12 petabytes of data. And I'm the primary person responsible for managing and maintaining all this stuff. But to be fair, one of the things I do keep track of is the data's, the size distribution of our archival holdings. And I wrote this nice little piece of code that for various sizes of files, how many they are, what percentage of the data, or number of files they are, the total volume of files in that size, what percentage of the total volume it is, and then the average. So this was just 3 years ago. We dumped out about 1.5 petabytes. Our average file size was only about 1.2 gigs, which is way too small. And it always bothers me to see zeros. That means there's a file sitting on HPSS on tape that has no size. That's a mistake. But last year we did a little bit better. We saved almost slightly more data, but we cut the number of files down by 1/3, so our average file size went up to almost 2 gigs. One thing I would like to do is, in my work in dealing with all these data, is try to use as many of the tools available to create as large as files as possible, because that's what fits on tape best. So how do we do it? Well, this was the way we used to do things up until just a few years ago. So we run the model on the supercomputer, dump a bunch of data onto the supercomputer's disk, and then stick it on a tape archive. Later, we go back to the tape archive, pull it off onto some local disk, either mounted on the supercomputer or some other resource. And then that, in a combination with some random notes, we do diagnostics, analyses, and things like that. And then we put this stuff on our web portal, which I'll talk about later. And if you recognize this slide, it's because I showed this at the CISL user forum in 2005. And believe it or not, this is how we did things up until about 2013. So one of the first projects that we did that changed this paradigm, if you want to call it that, was this thing we called the large ensemble. And what this was a set of about 150 simulations, almost 22,000 years of model time, that generated roughly 1.2 petabytes of raw model output. We did not do what I just described there. I'll go into more detail here in a second. The other one that started shortly after this, about 6 months into the period of the lens, was a last millennium ensemble. And this was roughly 40 simulations, but extending in model time from 850 AD all the way up through 2005. So roughly 1,156 years each. So that's a total of 46,000 model years and roughly 900 terabytes of model output. So between these two, that's over 2 petabytes of model-generated data. So this is our old workflow in a schematic form. Model run, HPSS, and then we just stop. And in between HPSS and the model run is disk, of course. And then we come back later, pull stuff off HPSS, do our diagnostics, generate what we call time series data out of the original model output, and do analyses. what we did for the lens in the last Millennium Ensemble was we did our model runs and just kept things sitting on Glade. And we had a nice set of disks set aside for us that I'll go into a little bit more detail. We did all of our diagnostics and our time series generation there, and then wrote that to HPSS. Except for a couple of early test cases, we did not write any of the raw model output to HPSS, only the post-process data. And we exploited some techniques for compression and other things that I'll go into. We saved all the time series data to HPSS, and then saved a subset of that to Glade in another partition. And then we did our analyses in the usual way. And this diagram is Sherry Michelson. So the way that we do things now, and has almost become standard, is this is the way the model writes out data. So the model steps through time, it dumps out a bunch of data at each model time, usually a monthly average, sometimes more frequently than that, for every output field. So field 1 may be surface temperature, field 2 may be surface wind or something like that, or if in the ocean, currents or salinity. For sea ice, it's like sea ice area, sea ice fraction, or sea ice thickness, that sort of thing. And as the model evolves, it generates a large series of files that contain all the fields at that time in a single file, one for atmosphere, one for land, one for ocean, one for ice, et cetera, et cetera. That's really great from a model performance point of view because it opens a file and then dumps a whole bunch of the stuff off, closes it, moves on to the next one. This is not that great for doing post-run analysis. Let's say, for example, you want sea surface temperature from the ocean. Well, you're going to get a whole bunch of additional data other than what you're interested in if you use these data. You're going to have to read off perhaps from tape or archive or read from disk, potentially hundreds and hundreds of files that contain what you want, but it's only a tiny fraction of it. So what we do is we do a transposition where we take each field and dump it into its own file for all the model times that are relevant for that field. So what we do is we take, say, surface temperature instead of mixed in with a bunch of other data. We put surface temperature in its own file all the way for the entire length of the run, with the caveat that if it's super high frequency, high resolution data, we might break that up into smaller temporal pieces. But typically we dump as much data into a single file as we can. One of the advantages, of course, is that you can access just the data you want and you get the entire time span, which really makes analysis great. Typically, a scientist or another user does not want all the data from a model component or from the entire model run. They just want to look at the pieces that are of their interest. So this format is much more efficient. It reduces the amount of data you have to download, the amount of data you have to store on your local system on disk or something like that. It's been my experience that it's very rare that someone needs more than a few dozen of these files compared to the hundreds or even thousands that come out of the model itself. The other thing we can do, also thanks to Sherry for that picture. So for the lens, what we had was we had a 400 terabyte disk partition set aside for us, I should say. And the bar chart there shows how much data the model was generating every one of these months, starting in January 2013 until we were pretty much done by the end of 2014. And you can see the quota there is way less. If you go over to the far right, that's the axis for that thing, or for that number. You can see we actually, in 2 months, we would have filled up that disk way before the model runs were done. So what that required was doing this transposition step extremely close to as soon as the model run was finished. And then the raw model output was purged off disk as quickly as possible. And there were a couple times when I had to go back to the people that are actually doing the model run and say, can you wait a couple days to submit the next job so I can get a chance to clear things off? And at one point, near the end, we decided to extend some of the original runs. And so because of the availability of the computer time, we came very close to filling up the disk. That was a bit of a panic over a weekend. I came in on Monday morning, we were like 97% full, and I was like, stop, stop. So the model runs were stopped. I got caught up, and then we finished. And then partway through, sometime in early 2014, the last Millennium Ensemble run started using the same disk space. So Dave Hart generously gave us another 100 terabytes, so the pressure was kind of off. And that disk partition is still being used today for CSM model development. However, last time I looked, it was now 900 terabytes, and about 880 was being used. So, as always, we can generate more data than we have space for. So, the final outcome was, as I mentioned earlier, roughly 1,200 terabytes of raw model output. But thanks to lossless compression that we applied to the output, we actually only had to save about 500 terabytes. So we cut the volume down by roughly half, and the number of files was roughly 1 million model output files. We got that down to about 275,000. So we reduced the number of files tremendously and then cut the volume in roughly half. And of that 500 or so terabytes, we keep about 120 of it on Glade semi-permanently for ready access for people that want to use it. But all the data is available on HPSS whenever anybody needs anything that's not on disk. Same thing with the LME. That actually compressed a little bit better because some of the higher temporal frequency data that we saved from the lens wasn't replicated in the LME, and I'll go into more detail about that in a moment. But once again, we cut the number of files way down and cut the volume way down. So this is what the compression buys you. So on the left is the different components of the model that dump out output. The temporal resolution is in the second column. The third column is how many different model output fields for each of those component and temporal resolution combinations. And then the three columns on the right are the best compression that we got. So you read 5% is roughly 20 to 1. So in other words, the final volume for that particular field was only about 5% of the original volume. The average is across all the different fields, and then the worst compression that we got is in the last column. So you read 88% is roughly 10 to 12% savings on the original model volume. The reds are where we got better than 10 to 1 compression. The blues are where we got between 10 to 1 and say 5 to 1, and the reds are where we got barely 2 to 1 or less. So the interesting thing is that the ice, land, and ocean, particularly the ice and ocean, since they only represent a fraction of the Earth's surface, they are not globally continuous fields, they actually compress really well. Even though the ocean data is large, a lot of it is ocean bathymetry and the land areas, which are basically nulls in the data set. Same with land, it's only 30% of the Earth's surface, and ice is only over the poles. There's a big strip in the middle that's nothing. Atmosphere is globally continuous, and the other thing is that certain fields compress really well depending on their complexity. So in other words, as you go from grid cell to grid cell in X and Y or time in T, if there's a lot of rapid changes like atmospheric precipitation, that doesn't compress near as well as like smooth fields like zonal winds at a high level in the atmosphere, because those don't change very much across X, Y, and Z. So these will inform us on, where do we get our biggest bang for the buck? As time has gone on, there are certain fields, for example, 6-hourly precipitation, they just don't compress very well. So the amount of CPU time it takes to do the compression may not be worth it. And we can flip on and off compression depending on what field. I can make a expert judgment on whether or not we want to compress something. The other downside to compression is certain access patterns of the data are somewhat less efficient depending on how you're accessing the data. Compression can sometimes result, when you access the data, it has to do some like on-the-fly uncompression, and if you're doing it in a weird way other than what the data is laid out in the NetCDF file itself, that can be somewhat inefficient. It may be more productive to convert the data back to an uncompressed format and then access it that way. But that's highly variable. It's hard to say. So the thing that we did at the end of the lens, actually during the last part of the last Millennium Ensemble, we had this new tool called PairiShaper, written by Kevin Paul with the help of Sherry Michelson and a couple other people of the CISL group. I guess it's not ASAP, it's Iowa G now or whatever the name is. But anyway, it's a Python tool that parallelizes across the fields so that you get much improved throughput. So it's basically the same operation as before, but now you can assign fields to different processing elements or PEs or sets of them, and that way you can really speed up the throughput on this. And this has been a real lifesaver. I'll have some timing numbers here in a sec. For the lens, doing this in the with the serial netcdf operator code could take hours, sometimes more than a day, to do significant volumes of data. I have yet to have any of these jobs take more than about 24 hours to finish, which is great. You can really speed up your throughput. And so I'm going to spend some time going over this. So here's a comparison of the same kind of data that I showed before. So there's the serial throughput is no better than 40 megabytes per second. With PairiShaper, we can get over a gigabyte per second throughput, which is roughly a 30x speed up. So what used to take a whole day now takes an hour, or what used to take 4 or 5 days now takes less than 1. And this has been amazing. This has been a real boon to us. And it works wonderfully. I've ported it to machines outside of NCAR. It's fantastic. And it's a key element of how we do our data processing and data management as we move forward. The yellows, which don't show up too well in here, unfortunately, those are where we get better than 10x speed up. The greens are where we get at least a 5x speed up. The blues are where it's actually a little bit slower. And the interesting thing about that is that's more related to the temporal resolution. So in other words, a single file may have lots and lots and lots of time samples in it instead of just one like the monthly data do. For example, the 6-hourly atmosphere data, the daily land data, and some of these ocean fields, and also the daily data from the runoff. So it has to do, as it's stepping through these data, it has to replicate the metadata a lot more frequently, so it kind of slows it down. Plus, these data tend to be relatively, like I mentioned before, complex, and that there's a lot of temporal variation in the data, plus the number of fields is relatively small, so you really can't exploit the number of PEs you're using. Plus, you may need to reduce the number of tasks per node because if you're not careful, you'll run out of memory. If you try to use all the PEs on a given node, you might have to break it up and do just a few nodes or a few PEs on a single node so you can avoid blowing out memory. So what we did is we used this PairiShaper for 2 sets of simulations we did at NERSC. It's called where we ran the model 10 sets of runs for every start year from 1954 to 2005. And we dumped out a tremendous amount of data, roughly 750 terabytes grand total. These runs were designed to experiment with how well the model predicts short-term climate change. Each one of these runs is only about 10 years long, but we ran a whole bunch of them, and then we repeated the set with having the volcanoes turned off for various scientific reasons. We cut down the model output stream a little bit from 13 to 11. The grand total was roughly 550 terabytes. So this is actually slightly larger than both the last Millennium Ensemble and the large ensemble. And we were able to do this in roughly less than a year, I think, something like that. Although we did have some fun when they took Edison away for 3 months and then brought it back up and it didn't work. And so that was entertaining. And then at the beginning of 2017, when Cheyenne first came online, the PI in charge of the decadal prediction project, Steve Yeager, wanted to increase the ensemble size from 10 members to 40. So what we did is we did 30 sets of runs for every start year. So that's roughly 2,000 new model runs, 1860 if I do the math right. We reduced the output set a little bit. The original model output was approximately 11 million of these time slice or history files. That's a lot of files. 1.13 petabytes, roughly 20,000 or 19,000 model years. When we got done processing all that, we reduced the number of files down by a factor of, 50 approximately, 45. And instead of 1.13 petabytes, we only saved about 410. And we managed to pull this off in 7 weeks, 6 weeks. So in other words, some of these projects that took years, we can now do in less than 2 months because of the ability to exploit the parallelism that PairiShaper provides us. So we can go through a tremendous amount of data in a very short period of time. But, I'll back up a little bit here. This was the result of this CSM, Software Engineering Group, workflow re-engineering project that was carried out primarily by the people you see here. Gokhan is now the ex officio member as the chief scientist for CESM. So this is what we did for the decadal prediction project. So there's CSM cranking away, writing data to GLADE. PairiShaper is being called by CSM, well, actually not CSM itself, as part of this workflow manager that Sherry Michelson is the real expert on and has put into place called Silk. And what Silk does is it kicks off the jobs that run CSM, and then when a model run is done, it kicks off PairiShaper basically, or the wrapper scripts that go around it, does all the transposition from time slice to time series format, and then when that's done, we HTAR each set of 10 runs, so runs 21 through 30, 31 through 40, 11 through 20, that sort of thing, and archive those to HPSS. So we reduce the number of files tremendously, and then eventually those get published to our Climate Data Gateway, formerly known as ESG, Earth System Grid. It is now called CDG. And then, of course, we can do our analyses from there. And this was, in some sense, a test bed for the upcoming CMIP 6 exercise, which I'll go into in just a moment here. So speaking of MIPS, so here's a nice logarithmic scale. This will give you an idea of how much these things have grown over time. I was actually in charge of CMIP 2 back in 2000, providing our data. I think I sent them like 3 CDs or something like that, which was great. It took an afternoon. I shipped them off to Germany, and they said, great, thank you. And then CMAP 3 came along. We generated roughly 100 terabytes of data, and of which we submitted roughly 10% to meet their requirements. Then came the infamous CMIP 5, for which we generated about 1.2 petabytes, of which roughly, or a little bit more than 10% more this time, but about 180 terabytes were submitted for the intercomparison. And then, of course, CMIP 6 is starting imminently, whenever that will be, soon, I hope. Estimates range roughly 5 petabytes of raw model output, of which we will submit roughly 2. So we'll actually submit probably a bigger proportion of the model output than we did before, but as you can see, that's roughly a 4x increase in raw model output and more than a 10x increase in the amount of data we're going to be submitting. The total CMIP 3 archive is roughly 30 terabytes, excuse me, not petabytes. So we provided roughly a third of the entire CMIP 3 archive. For CMIP 5, the grand total was roughly 2 petabytes, so we were roughly 10% of that. Both of these were done over a period of approximately 2 years. So a little bit more detail. For CMIP 3, we had 2 versions of a climate model. One was CCSM3, the other was our old DOE model called PCM. For CMAP5, we used CCSM4 and CSM1. Then for CMIP6, we're going to use CSM2. I have no idea exactly how many model years are going to be running or how many runs we're going to be doing for CMIP6. A lot of that is dependent on how much computing time we have. As CSM2's release continues to be delayed, that kind of reduces the amount of runs we can do. However, the request from the MIP folks has gone completely out of hand, haywire. So experiment classes are, what I mean by this is the kind of broad categories of runs that they would like the different modeling groups to do. So in CMIP3, that dozen was things like an 1850 control, where we keep the model state more or less fixed and run it out for a long period of time. Simulations of the 20th century, simulations of the future, and a few other things like that. For CMIP5, there's roughly 37 of those. And then for CMIP6, they're asking for roughly 150 different kinds of runs you can do with your model. The number of output categories, this is things like atmospheric monthly, atmospheric daily, ocean monthly, ocean daily. For CMIP3, there was 6 of those. For CMIP5, there was 18. And for CMIP6, they went 44. Different component and temporal resolutions. Sherry knows this well. The number of requested fields has gone from 137 to almost 1,000 to over 2,000. So that's how we go from 180 terabytes to 2 petabytes. The tools I used for these various things, for CMAP3, I used this thing, NCL, because primarily when you're submitting data for an intercomparison project, you have to add additional metadata, which I'll go into in a moment here, do some simple calculations, mostly simple, sometimes more complicated ones. And NCL is perfect for that. For CMAP5, I used a tool that came out of Lawrence Livermore called CMOR2 Climate Model Output Rewriter version 2. Based on the experience, we're going to be using a new tool called PyConform that is almost complete, that is analogous to PairiShaper, and then it's written in Python, it's parallel, and hopefully it will get us over the hump that we had with CMOR2, which was a serial code, where we had more model data than we could keep up with, and that became kind of a pinch point. PyConform should solve that problem for us. So once again, there's those data volumes, and hopefully, and I'm extremely confident that these new tools and exploiting parallelism will get us through CMIP6 without too much pain, but that remains to be seen. So here's the CMIP6 workflow. Here's your model run Glade. You do your diagnostics with this tool that does averaging and creates climatologies called PyAverager that Sherry Michelson wrote. Everything feeds through PairiShaper, then onto PyConform, and then eventually published to the ESG Federation, which is a collection of data or collection of nodes set up by the World Climate Research Program Working Group on Climate Modeling to distribute all these MIP data to all these different modeling groups and analysts and others. And then, of course, sitting on top of this is the Silk Workflow Manager. So by the time we get going full speed on CMIP6, all this will be automagical with as little human intervention as possible. That's the intention. I think we'll be able to do it. I'm more of a consultant and an advisor this time around. I've kind of gotten burned out on these MIP exercises. They're too stressful. So good luck to the people that are doing it. So this is what I said so this is what our workflow looks like now. So you have big iron goes to big disk, and you're wondering, maybe why is this 50 terabytes? There's your data processing engine, archival storage, and all these other things. Well, this is what I said in 2005 when I got to the end of my talk. So finally, after 13 years, we're almost there. We're about 95% of the way there. So that makes me very happy. So I'll go through this a little bit. Principles of data management. And you can, when this PDF goes up, this is a link. You can actually read this if you're interested. So here's the basic principles: policy, ownership, documentation metadata, which are critical, quality control, life cycle, stewardship, access and dissemination, and of course auditing. And this, I'll go through how we do things in CSM. First thing, policy. We do have an official data management plan. It's called the CSM Data Management and Data Distribution Plan. And what it does is it defines what CSM data are, ownership rights and responsibilities, data release and retention timelines, the standards we follow, the quality procedures we follow, and how we make our data available to the user community. So this is how the data is supposed to work, data retention. So for the first, as soon as a run is ended, approximately 100% of the data is restricted. In other words, the only people that have access to it are the principal investigators and their close collaborators. So they get first crack at writing scientific papers based on the model results. Then after 6 months, the data are supposed to be released to the wider working group and anyone else that the PI deems worthy of access to the data. But after 1 year, max time limit, the data are to be public. So anyone with access or an ESG account, CDG account, can access the data and it becomes fully public. There are no restrictions on commercial use. So if you want to take our data and make a product and make some profit of it, that's fine. Some of the European modeling groups are forbidden from doing that, which is unfortunate. However, once you get out to 5 years, we're supposed to reduce roughly 25% of the holdings. After 6 years, down to 50%. And then 7 years and on, we're only supposed to keep roughly a quarter of the data. We've never actually done that. We keep everything forever, which is the problem. And a little bit about metadata. So this is what the model dumps out for a given field, in this case, surface temperature. Here's the information that if you do an NC dump -H in the file, there's the name, the units in Kelvin, the long name, and the cell method, which tells you that it's a temporal average. For CMAP5, the exact same field, this is the metadata they asked for. This I would like to see as part of our standard output in the model itself. This is much more informative. This tells you much more information about what you need to know about this data set or data that you're looking at. It's got a standard name, which is a CF convention, climate and forecast convention name, long name in English, a little bit more information about what the temperature actually represents, and additional information. This is what Seymour stuck in there, telling you what it did to the data, and then plus some other information. Standard CSM global attributes, this is from the atmosphere. There's a few things in here like version and revision ID that are apparently empty. This is not terribly helpful. This is what we had to put in there for CMAP5, and this is much more descriptive. So it tells you the project was CMAP5, it's actually output, frequency is monthly, the modeling realm is atmosphere, came from NCAR, and then this is the meat of it, actually, the model ID and this reference here. This actually points to a paper you can read about that describes this data. And then their contact, and I actually get emails from this from time to time. The emails to CSM data actually go to me, acknowledgements. And then this is additional required metadata. And this is a much fuller and much more complete description of this particular data set. The key thing for CMAP5 is this thing, a tracking ID. This is a unique identifier for every data set. So if anybody has a question, I can always ask them, what's the tracking ID of that file you're looking at? Let me verify that it's correct. That's an absolute key element, because in some cases we had to redo some data sets because there was a problem found or a decision was made that the way we defined a particular field had changed, a different definition was better. This really is key to helping me get things straightened out. And then there's some additional information that I put in there, like, for example, who did it on what machine and what revision of the processing code was used. So if necessary, I can go back and look at that state of the model code. Unfortunately, since we don't have a subversion repo anymore, this is kind of a moot point, but that's okay. And how we do quality control, we run diagnostics like crazy. Each component has its own package, primarily built on NCL, and the scientists are the ones who give the thumbs up or thumbs down in looking at these things. This is the scientific quality. The data quality, or the data quality is more dependent on the NetCDF standard, and we try to follow that as closely as possible. How do we get this stuff out to people and how much? So here's some metrics from the climate data portal. As you can see, there's this big spike in 2012, 2013, and you're thinking, why is that? Well, it turns out, as part of CMAP 5, all the different modeling groups, or different core nodes of the Earth System Grid Federation, replicated our data at their center. So you have a distributed way with no single point of failure for all of these important data sets. So in looking at the metrics, these blue bars, that shows the activity of the people I knew that were the gateway managers copying all of our data to their gateway. So you subtract out that stuff and the CMIP 5 data, and so what you get is, note the change in scale, and you're like, well, okay, we're actually putting out roughly 40 terabytes a month on average over the last year or so. That's almost a terabyte a day flowing out from our HPSS to our users. That's not too shabby. You add it up over time, these are cumulative totals. The bluish gray shaded area is all of our data flowing out. We've now sent out over 4 petabytes of data over the last, 6, 7 years. CMIP 5 has kind of flattened off as people are anticipating CMIP 6, but you can see the not CMIP 5 data is growing, and that almost looks like an exponential curve to me, which is a little bit scary. And here's a depiction of where the people are that use our data, as one would expect. Heavy in Europe, heavy in the United States, Australia, and some of these, I don't know if you can see this one. I checked on Google Earth. That is actually a Russian research institute up there. I thought it was a little bit flaky, but no, I don't envy the person that has to work up there. And I also provide data support. Here's examples of some real questions that I've gotten from people. Some of these are interesting. Some are a little bit bizarre. The second one here is somebody who's probably from the GIS world, because they actually use coordinate reference systems. In CSM world, we just have a perfect sphere of, the Earth is a sphere of 6,378 kilometers radius or something like that. And what they're interested in is like digital elevation models and standard coordinate systems. That really doesn't apply to us. This was one of my favorites. And I had to point them to the Unidata software for reading NetCDF files. And there's some other ones. Now, these are actually a little bit more clever. This is where I point them to our papers that describe the model and our model experiments and our experiment designs. This is when I get questions from people who use R a lot. I have to translate, what is a brick and what is a raster, because I don't know R as well as I should. So here's some future directions, I think. We used to have a thing called the Mass Storage Advisory Committee that ended sometime around 2009, 2010. Given the stuff that we just saw in the Daily Beat today about quotas on HPSS and training, I think it's time to give this committee another chance. Because right now, HPSS is our limiting resource. Computing time's not an issue, really. People are somewhat of an issue, but everybody's multitasking, so we're getting good at it. HPSS is now the limiting factor, because we don't want to spend any more money on HPSS, particularly tapes, than we absolutely have to. So the more we can do in working together with the Mass Storage Group and CISL and the user community to make more efficient use of this, that would be to everyone's benefit. Also, I would really like to have SAM upgraded to include much more descriptive information about both GLADE and HPSS. My primary tool to look and see what we have on HPSS is HSI minus Q, double quote, LS minus capital RL, end double quote, and redirect that to a file. I've I used to do that daily, then I did it weekly, and now I do it monthly because it takes too long. But I don't think it would be good if I did that on the root directory. It would probably take a month to do that. But that's the only way I know of to really see what we have on HPSS. And you can do things like, tell me the project that each of these files are on and that sort of thing. But I would really like to see something out of SAN that says, here's what your growth is, here's how much data and where each of these people have on HPSS, what the projects are, what the growth has been, what the projections are going to be. If we see a big spike in archiving, how long until we reach day 0 on tapes, how many tapes do we have left, that sort of thing. Same with GLADE. We do a great job with computer allocations and being able to assess, do we need to slow down, can we speed up, what cues should we use? We need the same kind of tools for GLADE and HPSS. One of the things we need to do inside CSM is update the data management policy to reflect these various changes that have taken place. The current data management policy is from 2011. It needs to be updated. We definitely need to exploit lossy compression and use the ensemble consistency tester to make sure the scientists are assured that it's the same climate. Bit for bit is no longer a tenable requirement. It's just not realistic. And of course, I know Sophie very well. We're going to work closely with DSET and her DASH project. So as time goes on, we'll have these, golden standard model data sets that are part of DASH. In the longer term, it's not clear to me that the data portal model is sustainable. I have used the data sharing service that CISL provides for really large data sets. It's really nice to be able to put 10, 15, 20 terabytes on there, tell somebody go to it on Globus, and they can pull stuff down way faster than pulling it off HPSS, which is where most of the data that we have resides. Another thing we need to consider is having server-side analysis. In other words, run your analysis package on a Cheyenne node or set of nodes instead of trying to pipe all this stuff to your local machine. A little bit more radical is perhaps we just need to do the analysis on the model state as the model is running and keep that and forget just saving all this data that we could come back and look at later. And of course, the really radical one is do the minimum amount of data that you need to do your science and then go back and back up the model and rerun it so you can increase the temporal frequency or the resolution or something like that. So if you see something interesting, instead of saving, hourly full column atmosphere data for an entire run, you don't do that. You just run the model for those periods where something interesting happens. There's a lot of issues with that, but that may be the case. So here's an interesting thing just for fun. So if you look at NCAR's HPSS storage, which are the blue there, the solid blue line, and the light blue line is a trend. And then I actually have a table of all the different supercomputers that NCAR's had and their flop rate. You look at that over the last few years, you can see there the big jump from when we got Yellowstone there, and then a little bit, it was higher, and then Yellowstone went away, so now we're at, with Cheyenne at roughly 7 petaflops. And then there's our bytes held, and you project into the future. So sometime around, I think it's June 14th or is it June 15th? I think in 2025, we'll hit an exabyte, and then sometime in late 2029, we'll have an exaflop machine. The interesting thing is if you divide those two numbers, actually we're saving less and less data per floating point operation. So by the time we get to, I don't know what's after X, a yottaflop machine, well, actually won't be saving anything. Or maybe it'll be, the answer will be 42. And that'll be all that's all that it will say. So thanks to all the people that are part of this effort to do all this stuff and keep our users happy. And I'm happy to answer any questions.